This is section 5.3, conditional probability and independence. All right, so it says the probability that one event happens given that another event is already known to have happened is called a conditional probability. So when we see this notation, we read this as the probability of B, then you have a bar right here, straight up and down bar, that's a given, so probability of B given A. And the way we would read this one is the probability of A given B. So in the first case, if event A has already happened, what's the probability that B happens? And in the second case, if event B already happened, what's the probability that event A has happened? All right, and there's a formula to help us out. All right, so you look at these two events. In the numerator, you put the intersection of those events. Okay. You put the intersection. Whether it's B given A or A given B, either way, those two letters go on the top with an and symbol. All right, now based on what has happened already, so after the given bar, if there's an A, then we put probability of A on the bottom. If there's a B at the end after the given bar, then we put probability of B here. So let me kind of show you what it's like here in a Venn diagram, how we would find it. All right, find the probability of B given A. We take the probability of B and A over the probability of A. All right, so in a Venn diagram, what that looks like, let me draw my two circles. There's circle A and there's circle B. All right. Well, here, the top says the probability of B and A. That's the intersection part. So that's the green part. And we divide that by the probability of A, which is the entire A circle. So what we know from here is that event A has already happened. So it's got to be in circle A. All right. But B has also, or B, we're trying to find the probability that B also occurs. Well, what part of the circle is in A, but also in B? And that's the intersection part. So that's how we would find that. All right. So for example, all right, if there were 4 people in the intersection and there were 8 people not in the intersection, then the way we would find that, you would take the number of people in the intersection 4 over everybody that's in circle A. Well, 8 plus 4 are in circle A. So this would just be 4 over 12, or you could reduce it and say 1/3. That's how you would find it. All right. And in the second example, the probability of A given B equals the probability of A and B over the probability of B. So in a Venn diagram, I make my circles. A, B. All right. So the top part is, again, probability of A and B. That's this intersection here. Okay. But on the bottom, there's a probability of B. Okay, so that is this entire blue circle. All right. So event B has happened for sure. So we look at circle B, but what's the probability that they're also in A? Okay, so that's the intersection piece. So for example, if there's 10 people there and there's 6 people here, then you would take how many people are in the intersection, 10, over how many in total are in circle B. Well, you have these 6 plus these 10, which would be 16. All right, which you could reduce to 5 over 8 in that case. So that's the way we think about conditional probabilities. All right, now what about if there's no overlap? Well, if there's no overlap of the circles, then this numerator becomes a 0. because there is no intersection. All right. Let's go on to the next page. All right, it says, using data from the previous two-way tables, calculate the following conditional probabilities. Okay, so let's write these in proper notation first. So part A, probability that the person is male given they have pierced ears. So the way I would write that is I want to find the probability that someone is male given that they have pierced ears. Okay. So the way I'm going to find this using the formula, all right, we would take the probability that the person is male and has pierced ears over the probability that they have pierced ears. And give me a second, I'm going to redraw that Venn diagram for us so we can evaluate it two different ways. Okay. So I'm just going to go back and let's redraw this Venn diagram. So in our circles here, this circle represented males, and this circle represents pierced ears. All right, and we had 71, 19 in the middle, 84, and 4, and the total is 178. Okay, so it's going to be really, really easy if we use the Venn diagram here. All right, or we can actually use the decimals that we found, okay, up on this page. So if I use the decimal version, male and pierced ears, we got 0.1067. Actually, let's write it as the fraction. We got 19 over 178. So that probability is 19 over 178. All right. Now, the number of people that have pierced ears were 103 out of 178. Okay, so let's not use the decimals, let's use the fractions. Okay, well, if you notice, both the numerator and the denominator are both divided by 178. So those simply cancel each other out. So my final answer is 19 over 103. Now, how could I do that just using the Venn diagram? Well, how many people are male and have pierced ears? Those are the 19 people in the center. So if I just look at the Venn diagram, I get 19 people in the center. And how many people have pierced ears? Well, these 19 do, but so do these 84. If I add 19 and 84 together, that's 103. So it's much easier just to use the Venn diagram. So let's try question B just using the Venn diagram. So in question B, they're asking me to find the probability that the person has pierced ears given that they are a male. Okay, there are two different questions. All right. So here, the way I'd write it with the formula, I'd say the probability the person has pierced ears and a male over the probability that they're just male. Okay, so if we use the Venn diagram here, pierced ears and male, that's the intersection, so there's 19 people there. But how many people are just male? Well, you have these 71 are male, but so are these 19, because these two numbers are both in the male circle. So 71 plus 19 would be 90. All right, so 19 out of 90. And guys, even with these, you can convert these into decimals if you want. So 19 over 103 in part A, that's 0.1845 as a decimal. Okay. And 19 out of 90 is 0.21 repeating. So 0.211. I think it's much easier when you use the Venn diagram. All right, let's do question C. Okay, this has to do with the New York Times problem. All right. So part C, what's the probability that a randomly selected resident of the apartment complex who reads USA Today also reads the New York Times? So let's see if we can put this into probability notation. So we know that they read USA Today. So that's the given information. So given that they read USA Today, what's the probability that they also read the Times? All right, so let's look back at that question. All right. So if we look at our intersection, there's 5 people that, well, we can write this as the formula first. Okay. Probability that they read both New York Times and USA Today over the probability that they read USA Today. Well, what's the intersection? The intersection's 5. There's 5 people that read both, because 5 people out of every 100. Okay. All right. And what about USA Today? USA Today is circle B. So it's this. Well, how many people read USA Today? These 5 plus these 35. So if I add these two numbers together, that's 40. All right. So 5 out of 40. Okay, so given that they read USA Today, the probability that they also read the Times is 5 out of 40. Okay, so, or you can reduce it to 1 over 8 if you want, or as a decimal, I believe that's 0.125. So let's look at the next question. It says, students at the University of New Harmony received 10,000 course grades last semester. The two-way table below breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering and physical sciences, and health and human services. Okay, so here are their grades. People that got an A in courses offered by this school, and this school, course grades of B, course grades of C or below. So you know, and I know, that whenever we do a two-way table, it's important to make a totals column and a totals row. So let's just add these. Okay, so let's just go across first. So 2142 plus 1890 plus 2268. All right, so that's 6,300. 368 plus 432 plus 800. That's 1,600. 882 plus 630 plus 588. That's 2,100. If I add these down, okay, it should be 10,000 because they told me that in the problem. And it is. It's 10,000. So that's good news. Okay. Then we can add down how many people got A's, or how many course grades of A. 2142 plus 368 plus 882. And that's 3392. 1890 plus 432 plus 630. It's 2952. 2268 plus 800 plus 588. That's 3656. Let's add these three numbers to make sure they add up to 10,000 as well. So 3392 plus 2952 plus 3656. That equals 10,000 as well. All right. So it says consider two events. Event E, the grade comes from an engineering and physical science course. So if we look across at engineering and physical science, they gave out 1,600. Okay. So if I want to start to write this down, all right, I can figure out what the probability of E is. Okay. There's 1,600 grades that college handed out of the 10,000. All right. And you can do a little bit of reduction here. All right. You can cross those two out with those two. So this becomes 16 out of 1,000. You can make it a little bit simpler. All right. Or you can reduce it even further. You can say 8 out of 500. You could say 4 out of 250. Or you could say 2 out of 125. Oh, whoops, I messed that up. All right, that actually becomes 16 out of 100, which would be 8 out of 50, which would be 4 out of 25. Sorry about that. All right. Or just as a decimal, you can start with 1,600 divided by 10,000, and that is 0.16, so 16%. 16% of the course grades came from engineering, the engineering college. All right, and you can also, so what I'm doing here is I'm just looking across here. All right, and L here, we can find the probability of L. The grade is C or below. Okay, so if we look down here, all right, there was 3,656 grades that were C or below out of the 10,000. So that equals 0.3656 as a decimal. Let's just deal with the decimals because it's a little bit nicer. It's 0.016. So let's answer the questions here. It says find P of L. Well, we just found that. Interpret this probability in context. So we already found the value, so let's interpret it. 36.56% of the course grades last semester at the University of New Harmony were C or below. That's the interpretation of it. Right. So now let's do number 2. It says find P E given L and P of L given E. All right, so let's do the first one here. Probability of E given L. Let's write a formula for that. All right, so this would be the probability of E and L over the probability of L. All right. Well, we don't know what probability of E and L is, so let's find that up here. So the way I would find probability of E and L, that means intersection. Well, how many students were engineering students and got a grade of C or below? Well, that was 800. All right, so that was 800 out of the 10,000 students. So as a decimal, that is 0.08. All right, so if I'm going to just use the numbers I've already gotten here, the probability of someone being an engineering student and getting a grade of C or below, that was 8%. So I take 0.08. All right. Over the probability of them getting a C or below, that's P of L here, that's 0.3656. And if I do that on my calculator, I get 0.08 divided by 0.3656. All right, and that's going to give me 0.2188. Now there's actually another way to do this, just looking at the two-way table. Instead of asking yourself for percents, okay, how many raw number of students were in engineering and physical sciences, 800, and got a C or below? Okay, so 800 of them were there. That should equal 800 over, well, how many raw number of people got a C or below? Well, that's 3656. Okay, so if you notice here, if you do this, 800 divided by 3656, you get exactly the same number. So you can use the actual probabilities or you can use the raw numbers that are in the table. All right, likewise, let's do the next one, L given E. All right, so that would be the probability of L and E over the probability of E. You can use percents or you can use raw numbers. Now let's use raw numbers, L and E. So here's the L column, here's the E column, there's 800 raw people. And probability of E, you can just use the raw number of engineering students. That's 1,600. Okay, so if I do 800 divided by 1,600, that's the same as a half, which is 50%. If you wanted to do it the other way, L and E means the same thing as E and L. You could do 0.08 over the probability of E, which is up here, which is 0.16. So either way you do it, you're going to get 0.5. All right, so it asked me to interpret these. All right, this right here, this is the probability that what? What was E? That the student took an engineering course given that they made a C or below. This says something different. This is the probability that the student earned a C or below given that they took an engineering course. So question 3, it says, which of the conditional probabilities found in number 2 tell you whether this college's engineering and physical science students, that's the middle row, okay, tend to earn lower grades than students in liberal arts and social sciences. All right. So here, I would say it's the second one. I say it's L given E because, all right, given that they're an engineering student, there's a 50% chance that they got a grade of C or below. If you did the same thing with the other two here, okay, so for example, if I took 2268 and divided it by 6,300, all right, people in liberal arts, all right, people in liberal arts, 36% of this Okay, 36% of these people got a C or below. Okay. Here, 50%. 800 out of 1600 is 50%. And then the last one, 588 divided by 2100 is 28%. All right. So these are vastly different percentages. All right. So it says again, which of the following conditional probabilities tell you whether this college's engineering and physical science students tend to earn lower grades than students in liberal arts and social sciences? All right. So it's this one for sure. All right. 50% of students taking engineering classes earned a C or below. Given that they took an engineering class, the probability that they got a C or worse is 50%, much higher than the other two, if you were to rerun this with liberal arts or health or human services. Okay. So that would be your rationale there. All right, so number 3. You could say something like 50% of engineering grades were C or below, which is much higher than health and human services, where only 28% of students earned a C or below, and liberal arts, which was 36%. So you could explain it something like that. All right. So the next topic is the general multiplication rule and tree diagrams. So if we look at the conditional probability formulas, either way, all right, remember this is over an understood 1. Okay. So if we were to cross multiply here, because this is a proportion, if I were to cross multiply this and cross multiply this, then we get this formula. So if we don't know the intersection, but we do know this and we know this, then if I multiply these things, it's going to give me the intersection. Same way over here. If I take this times that, okay, it can tell me what the intersection is. And this is going to be really useful for a visual that we're going to make called a tree diagram. All right, so what does it mean? The rearranged formulas, that's these two, say that if we take the probability of an event, like here's your events, times the conditional probability, that's equal to the probability of both events happening. So that's the and statement. All right. So what is a tree diagram? It displays the sample space for a chance process that involves a sequence of outcomes. All right, so let's look at an exercise and figure out how to make this thing called a tree diagram. Tennis great Roger Federer made 63% of his first serves in the 2011 season. When Federer made his first serve, he won 78% of the points. When Federer missed his first serve and had to serve it again, he won only 57% of the points. Make a tree diagram to illustrate this exercise and answer the questions that follow. So when he makes his first serve, okay, so we're going to label this makes first serve. So there's only two options. He either makes his first serve or he misses his first serve. Now it tells us in the problem that he made 63% of his first serves. So on this tree, or on this branch of the tree, I'm going to put 0.63. Well, if he made 63% of his first serves, what does that mean about what's the probability that he misses the first serve? Well, these two have to add up to 1. Okay. So 63 plus what gives me 1, or 100? Well, that's 37. So there's a 37% chance he misses his first serve. Okay. Now, so like this is event A, and this is, you could call this event B if you wanted. All right. That's really not good to think like that. Okay, don't think about A's and B's because it's just going to confuse you. All right. So now it says when Federer made his first serve, so we're on this branch, there's two options from there. He can either win the point or he can lose the point. All right, so when he makes his first serve, when I'm on this first branch, he wins 78% of the points. So if there's a 78% chance he wins a point, what's the chance that he loses his point? That would only be 22%. Okay. Let's finish over here. When Federer missed his first serve, so now we're on this branch, he won only 57% of the points. So even if he misses his first serve, he gets to serve again, he can still win the point, or he can lose the point. Okay? There's only a 57% chance that he wins the point after he misses his first serve. So there's a 43% chance that he loses the point. So how do these formulas come into play? Well, the first branches are the probability of A and the probability of B. So here's your two events. Makes the first serve or misses. But these branches depend on the first one. So these numbers are conditional probabilities. These numbers are conditional probabilities based on this number. Okay? Or based on this branch. So what comes out here? Okay, let's think about what comes out. Okay, what does this represent? What does this branch represent? This is the probability that he makes the first serve and wins the point. Okay, there's your and statement right there. That's what's going to come out. And what does it tell us? How do we find that? We multiply. So let's multiply these numbers. 0.63 times 0.78. So 0.63 times 0.78, that's 0.4914. What does this branch represent? This is the probability that he makes the first serve and loses the point. So let's multiply those. 0.63 times 0.22. That's 0.1386. What you will notice is that these two values, okay, if I were to add those two numbers together, it should equal that. If I were to add those two numbers, they're going to add up to that. All right. Now, what does this branch represent? This is the probability that he misses the first serve, but he still wins the point. Okay, so you're going to take 0.37 times 0.57. And that is 0.2109. And this branch represents a miss and a loss. So I'm going to take 0.37 times 0.43, and I'm going to get 0.1591. And what you'll notice is that these two numbers add up to this number. All right, so let's go through these questions now. Part A, find the probability that Federer makes the first serve and wins. Well, that's this right here. This is makes and wins. So that's simply 0.4914. Okay. Next question. Find the probability that Federer misses and loses. So misses and loses. That's this one right here. Misses and loses. So that is simply 0.1591. All right. What do you notice about the probability of someone who makes the first serve and wins the point, this one, and makes the first serve and loses the point? they simply add up to the probability of makes the first serve, okay, which equals the 0.63. So last question, what do all the and totals add up to? So what do these four numbers add up to? Well, we said that these two add up to the 0.63, and these two add up to the 0.37. If I add those up, they add up to simply 1, or they add up to 100%. It says, what do the conditional probabilities of each branch add up to? Okay, so they're talking about the conditional probabilities. What do those two numbers add up to? Well, those add up to 1. And these two numbers have to add up to 1. Okay. So in each branch, these two added up to 1 as well. Okay. So these two add up to 1, these two add up to 1, these two add up to 1. And all four of these add up to 1. Right? That should be true in every tree diagram. In every tree diagram, that should be true. Yeah, they can get a little bit more complicated, but that's the general idea. All right. So now, we're going to go in reverse a little bit. So part A, it says, find the probability that Federer wins the point. Okay. Well, which one of these numbers involve winning? Well, this number involves winning, the 0.4914. What else? This one right here. Okay, so to figure out what's the probability that he actually wins, all we have to do is add up the parts that have a win in it. All right. So that would simply be the 0.4914 plus the 0.2109. So if I add those numbers up, that is 0.7023. There's a 70.23% chance that Federer wins the point. All right. Now, if this is the probability that Federer wins, how would we find the probability that he loses? Well, there's only two outcomes in tennis, a win or a loss on each point. All right, well, so the easy way would be, that means the same thing as wins complement. Loses is the same thing as the complement of wins. So we could do 1 minus the probability that he wins. That's probably the easiest way. So 1 minus 0.7023, which is simply 0.2977. So there's one way to find it. Or, since this tree diagram was pretty simple, all right, just you could add up these two parts. That part involves losing, and so does this. So I could add up the 0.1386 to the 0.1591. So 1386 plus 1591, 0.2977. Notice it's the same number either way. All right, next one's a little harder. Part C. It says, find the probability that Federer misses the first serve given that he wins the point. So let's write this the correct way. Find the probability that he misses given that he wins. All right. So since this is a conditional probability, but it's not one that we were given, we have to do this a little bit different. So let's use the formula. So in this conditional probability, these two events are misses and this is wins. So in the numerator it would be misses and wins over the probability of wins. So in our tree diagram, what's this? Misses and wins. So the probability that he misses and wins is 0.2109. 0.2109. And we said in part A that the probability that he wins in general is 0.7023. So you can get the first piece of information from the tree diagram, but to figure out the wins piece, you have to add those together. So if I did that, 2109 divided by 7023, you get 0.3003. So what does this mean? There's a 30% chance that he misses the first serve, given that he's won the point. What's the probability that he missed the first serve? Well, there's a 30% chance of that. Okay. If he wins, there's a 30% chance that he missed the first serve. Right. Now, part D. Find the probability that Federer makes the first serve given that he loses. All right, so if he lost the point, what's the probability that he made his first serve? So if we're going to write the formula up here, this would be probability of makes and loses over the probability of loses. Okay. So let's find makes and loses. Makes and loses here, that's 0.1386. All right, over the probability that he loses, we said that was 0.2977. So if I take 1386 divided by 2977, all right, that gives me 0.4656 if I round. All right, so given that he lost the point, what's the probability that he made his first serve? 46.56% chance. So these are a little bit harder. You just have to read the question very carefully, utilize your formulas, and utilize the tree diagram that you made. All right. So here's another example, another exercise. It says, many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't, which would be called a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does. That's a false negative. Suppose that we know the following information about breast cancer and mammograms in a particular region. Okay. It says 1% of women aged 40 or over in this region have breast cancer. So question A here says draw a tree diagram. I would do this naturally. Okay. So it says 1% have breast cancer. So there's a 1% chance that a woman has breast cancer. Okay, so I'm going to write that as a decimal. So if there's a 1% chance that they have breast cancer, that means that there's a 99% chance that they do not have breast cancer. So I took care of that. All right. Now the next bullet says for women who have breast cancer, so I would be on this branch. Okay. The probability of a negative mammogram is 0.03. All right. So this is a negative result. All right. So this would be what's called a false negative. All right. And it says there that there's 3% chance that we get a false negative. All right. So if that's the case, all right, positive results, positive meaning that the test showed that the woman has breast cancer. There's a 3% chance of that. That means there's a 97% chance of this, because those two numbers have to add up to 100, okay, or 1 as a decimal, 100% or 1. All right, so this would be considered correct. All right, that would be considered a correct decision. Right. So let's think about the meanings of these things. So this would be the probability that a woman has cancer and gets a positive result, which is a correct conclusion. So we're going to do that 0.01 times 0.97. 0.01 times 0.97. So that is 0.0097. This is probability that the woman has cancer but gets a negative result. So she thinks that she doesn't have breast cancer. So if I do 0.01 times 0.03, I'll get 0.0003. And again, this is the false negative. Very scary. So we took care of the second bullet there. Okay, it says for women who don't have breast cancer, so now we're on this branch, the probability of a positive result is 6%. So as a decimal, 0.06. Notice they gave it to you in different ways. Here it told you 1% in words. Here it gave you a decimal, 0.03. Here it gave you a percentage with the percent symbol. So I'm going to convert those all to decimals. I think it's easier. So positive result, a woman does not have breast cancer, but the mammogram says she does. So this would be incorrect. Okay. It's called a false positive. Well, if there's a 6% chance of that, there's a 94% chance that there's a negative result. And that would be a correct. All right, a woman does not actually have cancer, and the test says that she does not have cancer. So in a similar manner, this would represent the probability of no cancer, but a positive result, and a positive result. So 0.99 times 0.06 is 0.0594. Okay. And this would be the false positive. Okay. This is a correct. Okay. This would be the probability of a woman not having cancer and the test showing that she's negative for cancer. Right. So 0.99 times 0.94, 0.9306. And this is a correct conclusion from the test. All right, so that's part A. Draw a tree diagram. We did that. All right, part B. All right, let's answer part B. Find the probability that a woman selected at random has breast cancer given that she tested positive. So let's write the correct notation. Find the probability that she has cancer given that she tested positive. All right. Sometimes it's easier to do the given part first. Well, what's the chances that she tested positive? Well, here was a positive right here. It had a positive in it. And this one has a positive in it. So I need to add those two numbers to make up the denominator. So I add 0.0097 plus 0.0594. That's the chances that a woman tested positive. Now, of these two numbers, which one also has the cancer? Well, it's this one up here. It's the 0.0097. So I would take 0.0097, and then if I add these, 0.0097 plus 0.0594, that's 0.0691, and then divide them, 0.0097 divided by 0.0691, okay, and that's 14.04%. Okay, so given that a woman, so this is kind of good news in a way. Given that a woman tested positive on her mammogram, there's only a 14% chance that she actually has cancer. Okay, given that, so she went to the mammogram, and the mammogram said that the mammogram had a positive result. But there's only a 14% chance that that woman actually has cancer. So that's a little bit of good news. So, all right, let's do part C. It says, find the probability that a woman selected at random does not have cancer, so no cancer, given that she tested negative. Well, which parts have negatives in them? Well, there's the negative and there's a negative. All right, so in the denominator, think about this as kind of like a fraction bar, the given as a fraction bar, just sideways. Negative comes second, so negative goes on the bottom. Just add the 0.0003 to the 0.9306. So if I add those together, I'm going to get 0.9309, I believe. All right. And of these numbers, which one is no cancer? Well, it's this one, no cancer and negative, 0.9306. Okay. So those numbers are so close to each other, this decimal is going to turn out to be something really close to 1, 0.9306 divided by 0.9309. Okay. So this turns out to be 0.9997. So there's a 99.97% chance that if a woman tested negative from her mammogram, that she actually does not have cancer. That's pretty strong. All right, if a negative test result comes out on your mammogram, then you have a 99.97% chance that you actually do not have cancer. Right. And lastly, part D. It just says, what's the probability that the mammogram shows the correct result? So the correct result would be this. What would be correct? Well, correct would be getting a positive result, okay, and having cancer. Okay, that would be correct. Or getting a negative result when you don't have cancer. Those would be considered correct. So the probability that I get a correct result would simply be 0.0097 plus 0.9306. So when I add those, okay, that is 0.9403. Okay, 0.9403. Chances we get correct results are 94.03% of the time. All right, which is pretty good. Okay, pretty good. So hopefully that exercise helps you understand how to do the tree diagram and how to answer questions. You need to be very careful and slow when you read the questions to get the correct notation, which allows you to figure out what numbers to put where. All right. Now, this is one of the hardest things for students to understand. Independence. All right. It says two events are independent if the occurrence of one event does not change the probability that the other event will happen. For instance, if you toss a fair coin twice, the second flip of the coin is not affected by the first flip. So the two tosses of the coin are independent of one another. Okay. Now, it says this: two events, A and B, are independent if and only if, which means this is a two-way biconditional. All right. The probability of A given B equals probability of A, or if the probability of B given A equals the probability of B. All right. An easier way than remembering this formula: two events are independent if the probability of A times the probability of B simply equals the same thing as the intersection. Okay, I always like to remember this one. Okay, I like to remember this one. If this is true, then the two events are independent. Independent does not mean mutually exclusive, by the way. It has nothing to do with mutually exclusive. Okay? So for instance, if you see a Venn diagram and you see something like that, it doesn't mean that they're independent. It means they're mutually exclusive. Okay? This has nothing to do with independence. Independence has to do with the formula. So, it says here that the two-way table displays data on the gender and dominant hand of each student from a simple random sample of 100 Australian high school students who completed a survey. Are the events male and left-handedness independent for these selected students from the sample? Justify your answer in 3 different ways. So to figure this out, we need to use numbers. So they're asking me about the events male and left-handedness. So let's first find the probability that someone's male. So male, there's a 46 out of 100, 46 people were male out of the 100. So as a decimal, that's 0.46. What's the probability that someone is left-handed? And so we're going to look across the left-handed row. 10 people out of 100 were left-handed. Okay, so that's 0.10. Now, they're asking, are these two events, being male and left-handed, independent? Well, let's look at some other numbers that we can get from the table. What's the probability of male and left-handed? So looking at our two-way table, how many people are male and left-handed? Well, there's 7 out of 100. So let's ask ourselves the question: does the probability of male times the probability of left-handed equal the probability of male and left-handed? Well, if I take my 0.46 times my 0.10, does that equal 0.07? Well, if you do this in your head or in a calculator, this turns out to be 0.046. So ask yourself the question: is that a true statement? Does that equal that? And you'll say, no, they don't. Those two numbers are not equal to each other. Therefore, male and left-handedness are not independent. So they affect each other. The dominant hand and gender affect each other. They're not independent. Okay? Because these two did not equal each other. If they did equal each other, then we would consider them independent. Okay? Now you could have done this a different way other than using that formula. And here's what I mean. Okay? You could have asked yourself this question. Does the probability of male given left-handedness, I'm just going to use LH, does that equal the same thing as the probability of male? Okay. Well, how would we find this part? All right. Well, in the denominator, we would put left-handed. Okay, so how many people are left-handed? Well, there's 10 that are left-handed. And of those 10, how many are male? 7. Does that equal the same thing as the probability of being male? Well, the probability of being male is 46 out of 100. So is that true? Well, 7 out of 10 is 0.70. 46 out of 100 is 0.46. Those do not equal each other. Okay? So since this does not equal this, they're not independent. Right? Or you could have switched it up. You could have done it this way. Probability of left-handed given male, does that equal the same thing as probability of left-handed? All right. So how do you find this out? Left-handed given male. Okay, well, how many males do you have? 46. And of those 46 males, how many are left-handed? 7. Does that equal the same thing as a probability of being left-handed? Okay, the probability of being left-handed is 10 out of 100. All right, so if I do 7 over 46, that gives me 0.152. 10 out of 100 gives me 0.10. So these do not equal each other. And since those don't equal each other, then we would say that those events are not independent. So you can do it any one of 3 ways. Okay. Personally, I like this way. This is the formula I like to remember. It's the easiest way for me. All right. And on the last page here, little note about mutually exclusive and independence. All right. It says we cannot simply look at a Venn diagram nor read the description of the event to decide if 2 events are independent. But here's what we can say with absolute certainty. If 2 events are mutually exclusive, they are not independent. Okay? So what that means, that first statement, if I have a Venn diagram, if there's no intersection between them, I know right away that they're not independent. Okay? Now, if they tell me that 2 events are independent, they are not mutually exclusive, which means that if I know 2 events are independent, there has to be some overlap of the circles. Okay? But not every Venn diagram where 2 circles overlap means that there's independence. Like here, if we did a Venn diagram for this one, there would be overlap. So it's not guaranteed that they're going to be independent. Okay, I just know they can't be both. Right? 2 events cannot at the same time be mutually exclusive and independent. Okay, they're either one or the other, but most times they're actually neither. Okay? Most times they're neither. Right. The only way we can figure out if 2 events are independent is if we do the calculations. We have to do the calculations. Very, very important. All right. So they can't be both. They can be one, they can be mutually exclusive, or independent, or neither. They cannot ever be both. That's the important takeaway. So this video was kind of long. Apologize about that. A lot of probability calculations, and hopefully most of it made sense. Go back and review it if you need to, and watch this as many times as you need to make sure you understand these laws of probability. Guaranteed they're going to come up again on the AP test.